Well, good morning. It's scary for me to be here because I'm dealing with a lot of great minds in this whole room, and I'm that gremlin. I'm that guy in the data center that when you call up and say, hey, I need a piece of software or I need a memory stick replaced, I'm the guy who does that. And so what I wanted to share with you is that the work that we all do matters. It matters to the people of the world, right, that use the applications and the software that we all support and that we run. And it's very easy to abstract the work that we do from the physical space. For instance, we hear about cloud computing as if it's manna from heaven, right? I sit on my laptop and all this data streams to it, and it must come from somewhere. But in reality, it comes from a building that was made with wood and concrete, and there's fiber, and there's people inside of it that actually provide that level of support. And what I wanted to do is share with you, administrators, right, what it means. So for instance, think about it like this. You call up a guy like me and you're like, hey, I got this server, I think it's got a name like this, or here's my cluster group, right? I've got 2 Walmart supercenters inside my building, and I need to go find that thing, and I need to go work on that thing really quick. And you're like, come on, I need you to do it. It's a really, really big thing. Scale is a really, really big thing, and there's a lot of people that are working on this. They're really, really big problems that we have to solve. So at Facebook, we're driven by a need to scale. Most people that make applications, they want to make a difference in the world. They want to share their knowledge and their learnings and the things that they're doing with other people and help those other people be more and more successful. Even the speech that we just heard from Ted, right, was like, hey, help other people. You know, it matters what you're doing. So we're driven by a need to scale because, you know, at Facebook, we realized that the problem is bigger than just us. So we created, like, the Open Compute platform. We're founding members of that. And there's a whole lot of work that needs to be done. Scale is a big problem, right? It's bigger than just Facebook. You know, and it takes all of us to work together because the applications that you support, that you manage, that you run, right? The world's waiting to use them. The world's waiting for you to help make that difference. And you can't do that without the infrastructure to support all of it. So our scale, 864 million daily active users, right? We have over 1 billion users on our platform. If you look at our monthly, 1.35 billion, but guys, there's 7 billion people in the world and counting, right? All of those people, right, they're not all in the United States alone. They're everywhere else. We need to put infrastructure in other places in the world. And again, the cloud, the virtual machine, those are real computers. Those are real things living in buildings that need to be cooled, need to draw power, and need to be supported, managed, and operated. So we did this first, and it didn't work out too well. This is a lifetime of learning from a whole lot of people. You know, when you got an infrastructure our size, there's always broken servers. There's always pieces of software that go down or really misbehaving, right? In most cases, systems that are engineered, you know, to try and self-remediate and stop these issues, but it doesn't always work that way. And there's impact to the people, there's impact to the site. What I want to share with you today is that the small things matter. The small things really matter. One of the things that you can get into when you start operating at scale is operational laziness. All of a sudden, you think to yourself, it's okay that that's down because, you know, I'm resilient, not redundant. You guys all know about the tier 1, 2, 3, and 4 data center space, right? Let's go ahead and sell what we do to a bank, right? I need tier 4 data center space. That means I've got 2 servers for everything, right? I've got 2 power inputs, right? I've got 2 generators. I got 2 of everything. Yet I still fail all the time. Everything goes down. So redundancy isn't the key. I don't have enough money to buy 2 of everything and then continue to scale throughout the world. What we started doing is thinking about resiliency being the key. So to do that, we had to get rid of all of our sacred cows, right? And our filters that we started to work our company with and start analyzing what we're doing and how we're going to scale. Because don't forget, Facebook started really, really small, right? And we all did what we knew, right? So once you do what you know, and then you grow past that, then what do you do, right? You can't just always say, well, I've always done this, so let's just keep doing that, because it doesn't scale, it doesn't work. So we said, okay, complexity creates waste. the more complex it is, the harder it is to troubleshoot. Like when I was working in network engineering at Microsoft, network operations at Microsoft, the engineers put it all together, and I learned a couple of things. The 3 C's of troubleshooting, right? All the academics know this. In the lab, it worked because configuration, configuration, configuration. Every time you run on a network and you're trying to look and see what's wrong and figure out what the problems are, it's almost always configuration, configuration, configuration. In the lab, it worked like this, but somebody has changed something on the operational network, right? And then we started to put all of the information and data and everything we wanted to do in one box. Like, think about the old 6500s with a SOUP 1A and a CSM in it. Next thing you know, I've got all these things happening. I've got load balancing and everything happening within a site, a switch that should be switching, but it's actually routing. When something goes wrong, how do I figure it out? How much time does that actually take? Have I really saved any money with this outage that now has extended into days because I simply couldn't figure out where the problem was? So we started thinking about that. Separate these things. Make them their own failure domains. Make them unique, right? Then we talked about resiliency is better than redundancy. 2 power supplies that go into the same room that starts on fire leaves your data center down. Does anybody remember the Fisher Plaza issue here? They were really open, and they shared that, right? And it was a really, really eye-opening experience for everybody in our industry. We thought we had this covered. We thought I have redundancy. What I didn't have is resiliency, right? And so that's the way our industry is starting to move. It's starting to shake. When we talk about the pager, right? I think about sysadmins with pager, and that's cool. Then I think about me with pager. I have to get up and go somewhere. I have to go into that data center, and I've got to go find out what the problem is. My sysadmin, fortunately, and I think it's good, you guys get to sit behind the desk and be there and be like, okay, I'm going to go tell Ken to go do this stuff. That's hard, right? It's harder than you think. And then you're frustrated with me because I don't speak your language. There is a separation of church and state right there. You talk about cluster. I talk about a physical location, right? So all of a sudden, we're on the phone troubleshooting a problem. It's a relatively complex issue, right? So how do we change that? How do we make us all speak the same language and get on the same platform? So I'll be showing you a little bit about that. But more specifically is this. I don't know everything. You don't know everything. We are doing things that people haven't done before. Large companies to small companies can contribute, can talk, can share, can simply just work with each other to figure out how to solve some of the problems that we have. We have research, right? We have some small startup company that's got 2 or 3 people that are doing something amazing that might actually fit into scale. So at Facebook and everywhere else that I've been, what I'm really happy to say is I've seen everybody say, you know what? It's pretty good, but could we do this better? Could we do it better? And I don't know exactly what I'm doing, so maybe I can talk to somebody else, and maybe they can help me out. So that's what we do with Open Compute. That's how we think about Open Compute. So with that being said, we started looking at the data center as a complete ecosystem. We said data centers are expensive. Data centers were running really high PUEs in the past. We put all this redundancy in there, yet we still had outages. We couldn't figure out how the servers were symbiotic or in symbiotic relationships with the data center, right? And what's all the software that we got to work on just to monitor and break fix our server? And on top of that, there's this application layer, right? That you all run, you manage. You want it up, you need it to be working. But how do you do that? How do you monitor that? Do you just look at metrics, right? It's more than just looking at the metrics. It's more than just figuring out how to shard this database and figuring out how to get, Hadoop or Haystack a little faster and a little better. People on the other end of this are waiting for us to work together and make it efficient, make it up, and make it run. Think about this. We're awake here today, but they're going to sleep, let's say in Japan, right? So while as I move through my day, these people are going to sleep and waking up at all the times. Our applications now are global. All of us, we're doing global work, and they need to be up and they need to be available at all times, because when I go to bed, right, somebody else is waking up and somebody else is using it. Gamers in Europe, actually, I was talking to the guy that did Destiny, the Xbox game. Apparently gamers in Europe are really awake pretty late. No wonder they start work at 10 or 11 o'clock in the afternoon. So our data center, we looked at it as a vertical stack. There's a lot more substacks underneath here. There's a lot more things that we could do. What I want to do is focus a little bit on what we've done with application. But then I'm going to talk to you about in our data center space, in the physical structure, in the cloud, what we've done. We've looked at software. How do we manage? How do we run? How do we operate? How do we monitor? How do we alert? When we look at our servers, how does that fit in with this software and this monitoring, right? And then we look at our data center, how does that fit in? We made this vertical stack of these 3 boxes, and we said they all have to interoperate with each other to deliver resiliency. Redundancy is not our key anymore. So for instance, in the software space, it really has to do with data center tools and workflow. Now, you should know that we implemented HHVM, right? 50% of our front-end servers are now running HHVM. Very fast compilation. We have 5 times less servers in our front-end fleet now than we had before we did that, right? We monitor our application weight. At Facebook, we're always iterating. We're bringing on a new service and a thing like that. And our application is a relatively monolithic thing with lots of little parts that feed and are integrated with each other. It's a relatively big problem. My problem is, how does that all run on the data center space and in the servers? And how do I keep one server from actually causing a problem for everything else? And how does our application actually increase in its weight, its need for workload, as new changes are made? If you think about it, I make one change, but it affects 200 billion connections. That kind of heats your data center up pretty quickly, right? We draw a lot more power when something happens. We put out this new video, and everybody was looking at the video of their time on Facebook. We spent a lot of time saying, okay, how's that going to work from an application standpoint? But more, how does that work from a data center standpoint? What happens when these procs spool up, right? What happens when my disks start really going fast, right? What happens when my power draw goes? Are we going to drop some rows in the server? Are we going to lose service? And these people don't get to experience it? Application-wise, system admin works great. But what if your physical infrastructure doesn't work well? So we started making a lot of improvements there. One of the great things from a sysadmin standpoint, we used to have a notion at Facebook of SRO and SRE. I saw some really cool bomber jackets, by the way, with SRO running around here yesterday. So whoever that is, it's a really good jacket. These guys are the first line of defense. They're the ones that are monitoring it, right? They have their computers, they have their pagers, and they're looking at the application, or at least the piece of the application that they care about, and something happens. And they keep getting interrupted with that something, right? So they can't go make the business better because they're busy working in it. It's hard to work on your business when you're working in the business. And at Facebook, we were really young. We had a couple of different co-location spaces. We had a space in Virginia and a space in California. Expensive power, right? Hard to maintain, and not a lot of space. But we knew we were going to grow, right? So one of our SROs, he said, in my copious free time, in between all these fires that I keep putting out, I'm going to start documenting the issues that I've had and what I've done to remediate it. Then I'm going to start making some little scripts so I can just run those, right, when it happens. And over time and over scale, it became such a hard problem. One person couldn't do it. Then you have a whole group. You have 20 or 30 or 40 people now, and they all have to have this carnal knowledge of your application, right? So what we did is we compiled all those scripts into a tool that we call FBAR, right? It's Facebook Auto Remediation. We actually wanted to call it FBAR, but we couldn't figure out what to do with the U, right? But you all know as sysadmins, like, this is FBAR, dude. I don't know what to do with this thing. So we did everything we could to come up with a U terminology, but so now it's FBAR, right? So Facebook Auto Remediation basically retrieves a list of outages. As for instance, I have a server that is just not live anymore. It's not pingable. So FBAR will pick it up. It'll go through the first remediation plugin, which is like, well, send a Pixie reset or something like that. Let's see what we can do, right? Let's try and re-image this. Let's try and get this alive. 2, 3, 4, 5 different layers of fix before it gets into a human's hands, right? That work alone, compiled and put together in a very cool way. We make a daemon that runs on the machines and keeps, putting information out, and then we scrape that information from a server and say, okay, let's go move this into all these other different tools that do things like imaging and rebooting and all of this. So it's really separated, really resilient, and it actually runs also in the data center space. Highly distributed. But the thing is, that saved me. Have you guys ever rebooted like 100,000 servers before? There's a couple ways to do it, right? You can go get a whole bunch of your friends and your neighbors into your data center, but it depends on who you work for. You might not even get them in the data center. You could throw breakers, right? You could get one row at a time, or you could go out to the air brake in the big utility yard. You could pull that and do it. It's a hard thing. A lot of guys, a fundamental argument that I get in all the time is IPMI. I don't think we need it because I think that I'm allowing. Oh, did I get something there? Oh! I was really thinking I was going to get booed because I'm getting booed everywhere else, right? The big thing about this is like no single server should be so important that your application suffers because it's down, right? That's a really fundamental thing with resiliency. And as long as we keep it to where you can access every server at each server every time through, let's say, either a fiber or hopefully a copper neck, right? We don't force resiliency into the mix. We don't force us to think about how we distribute machines physically. We don't force us to think about how we distribute our application on something. Other companies have a thing called a Borg that actually works really well, and you disassociate your application from compute resources, from hard drive and memory. It's just disaggregated, right? So you don't need that. Do you know how much money it costs to outfit an entire data center with copper cabling to every single server that you might use once in the three-year life of that server? Right? Millions and millions of dollars that I could put into more infrastructure in, let's say, a country that doesn't have it. I could put that money into something else that allows me to grow and expand our infrastructure footprint and reach more people. Because after all, the work we all do matters. It's applications that get to the masses, that get to the people, and it makes their lives better, fundamentally better, no matter what it is you're doing. That's what we are doing with the internet. That's what we are doing with all of the applications that we manage, run, and use. This was a big deal. 50% of the tickets that came into the data center space went away. It went away. Now we're working on making it faster, though, because maybe a day could go by before it goes through all of its iterations, right, and brings that server back online. By the way, at Facebook, we have hundreds of thousands of servers like some other folks. But what do you think our percentage of machines in repair are right now? Like, quick number. 3%? I heard 3%. Do I hear less than 3%? Right. Well, in the 0.06 to 1% ever range. Right? Used to be 10. When I was working at another company, somebody said, you guys are 10% failure rate? You know how many other extra servers I have to buy because of that? Just to keep my application up and running? You know how much money that cost? I didn't have a clue. I didn't care. I was doing push-ups while I was rebooting SQL servers, right? You know how long they take to come back? Right? And then I have to prove that I had it up and all these services were running and Windows load balancing service was working. I had to prove that, right? That was pretty difficult times. But I got really buff. And then the world has changed. We must be doing better, right? So when I started this thing, I talked about we needed a common platform to talk on, right? We have to get our system administrators working with our facilities organization, working with our data center guys, working with our server guys, working with the application owners, and just everybody working together with a common and fundamental understanding. One thing that we did, and we've been working on this for the last 2.5 years, we made an engine that we called DC Maps, and on DC Maps we built several different platforms. One of the platforms is called Cluster Planner. Now, I would use this little laser pointer, but it only works right here, right? So I'm just going to point it out. If you look at the red areas where it says like 04F and 07F, by the way, that's one of our data centers, and F stands for this side of the aisle, which is face, and B stands for that side of the aisle, which is book. That took us about 4 weeks to actually figure out how we were going to name our aisles. I wanted north and south. But they're like, well, we're in a data center. You don't know which way is north and south. It's like, oh, God, Anyway, what we do here is our application owners go to a group that they call CEA, right? And CEA is an analysis team. They're all data scientists, right? And they are the ones who control the purse strings. They say, oh, you want a 750 gig hard drive? No, I lie. You want a 3 terabyte hard drive? 3 terabytes, but you only use 2 gigs, right? Why do you need that? So they control the purse strings. They control the compute that the application owners are asking for. They control the memory and the hard drive that the application owners are asking for. And they work with them and say, OK, if we had this much compute memory and hard drive space, what machines would it work on? If you look in the lower bottom, the bottom where it says Cluster 12 front end, you'll see machine types. So one of our application owners needs some machines. They look like this. So they plug that in. CEA does their work. They put it in here. The data center is represented by the colorful blocks in the middle. That's all the open space. That's all the racks. That's the power draw that they take, all the compute resources that they have, and everything is actually managed through here. And I can do a Shift Q, and I can get that all in 3D. So for instance, I can actually take a look, and I wish I was smart enough to actually put this together in this presentation, now that I'm thinking about it. I can put this together, and I can show you the physical profile on the floor of every server that is rebooted in the last 5 minutes in red, right? So all of a sudden, like for instance, I don't know if any of you ever read about the sauna sev that we had in the Prineville data center, meaning it began to rain in our data center. I was at the rodeo, just had 3 or 4 beers, and the bull riding was just about to start. I'm like, jeez, right? I had to run in there, and you would walk through the data center, and you could see your footprints in there. We had a humidity issue. We had a microburst thunderstorm come through. First time we built an open compute data center. We moved too slowly. And next thing you know, though, I had SRO calling me and saying, we just lost 30,000 servers. I'm like, what? No way, right? Then I'm like, I am so fired right now. So we get up there, and we start taking a look at this, and what we realized is that we weren't as smart as we thought we were. We had rows and rows of servers already down, already out of service, but we're so resilient, we didn't care. Somebody else had them down for whatever reason. So my SRO guy, he just ran a script, pinged everything, and said, these are all the servers that are part of the outage. Yeah, they're not. So my team ran around like crazy trying to fix all this stuff. What was really broken, right, was maybe 10,000 servers. Still doesn't suck, but it doesn't suck as bad, So at the end of the day, we started really thinking, that's a problem we have. You talk about cluster, you talk about machines, I talk about a physical location. And so we really spent a lot of time doing this, even from a facility standpoint. If you look on the left-hand side, right, that's the Prineville data center, that's our MSBs and our SBs, because, by the way, the cloud requires power and energy, right? It's not just, again, just falling onto my laptop from nowhere. So as I put more and more servers in different configurations, I draw power. It's red in 04F because I have an over-allocation of power in that row. So what that really means to me is if my servers spool up for whatever reason, or if I change the service that's on that server, right, I may be drawing more energy. So maybe I have a rack that draws 12 kW when it runs this application. What if somebody changes that up in the same rack, new application, what's my maximum power draw? And what we try to do is make sure that we don't strand power, right? Power is money. It's a huge amount of money. And you think about the efficiency of a data center, right, which I'm going to get into. If you use 1 megawatt and lose 1 megawatt, that's a whole lot of money gone. So it pays to be green, and it pays to be efficient, and it pays to figure out how to build an infrastructure where you can maximize the use of your compute resources, maximize the use of your space, but more importantly, maximize the use of your energy, because that is where your ongoing operational cost lies. A lot of people forget to think about that. And you'll hear your facilities manager yelling and saying, I've stranded 2 megawatts worth of power. If you don't know, I want you to know, that is a big deal. That is a lot of money gone every year. So then we moved into our software stack even further, and we started thinking about, there's a lot of things that a server technician on the data center floor has to do. So when I came to Facebook, almost 5 years ago, we still had media carts that we were moving around. We'd stack motherboards on, they'd fall off, and we had Dell and HP servers, and we were dealing with all of them and trying to help with troubleshooting. And it was really just like any normal business, that you run. But we knew one thing: we're going to go to scale. We're going to grow. So as we got ready to build the Prineville data center, we started looking at how does our technicians work. right? I don't know if any of you guys have ever dealt with this, but you know, I buy servers, I pay a percentage on top of the servers for the support from whatever OEM has it, and they give me parts, and I have to go through all this, you know, hoops and machinations when I get rid of parts and bring new parts in, and sometimes I don't get enough, and then on my servers, they're dead for a long time. But at the end of every year, I still pay $2.3 or $2.4 million for all the parts that I lost. I know I didn't lose these parts. I know they're somewhere. Point is, inventory tracking isn't tied to server repairs. So we started looking at that, and we said, okay, we got to do parts check-ins, inventory transports. We got to have the dashboards that show us where we're at and what we're doing at any time. Our failure analysis, right? Like we just talked about with FBAR. And then shopping carts. Like, I need to get a part, I need to put it on a cart. Oh, carts. Media carts aren't carts, right? So if you look in the far right, there's a little cutout of a cart that we made. That's actually available via Open Compute as well. That was the first project we made and said, I need a cart with drawers and ESD capability so I can manage and move a lot of parts safely on the data center floor. Because again, and I'm not kidding you, okay, this room is a single data hall. It's actually smaller than a single data hall. Okay, in one of our buildings, there's 4 of these in a row. So if you leave your screwdriver over there, and your server that you're working on is over there, it's kind of a problem. In the meantime, you got your SRO guy going, hey, dude, when are you going to get that done? When are you going to get that done, right? We need to be able to keep everything together, keep it. There's a lot of moving parts, so we need to keep everything accounted for at all times. So we started a ticketing system. We used Salesforce at the time, right? We put this ticketing system together that FBAR would actually feed into. You know, over time, we've grown and iterated and gotten better. Now a technician comes to work here today, they grab their laptop, which is sitting on their cart, and they open it up and they look at sort. And sort says, you've got 32 servers failed. Excuse me. The diagnosis looks like it might be 14 motherboards, 3 of these, 2 of these, 1 of these, and then 6 of those. So he turns around, he grabs them out of the bins that are right behind his cart, he scans them into his cart. Now I'm owning those parts. I know where they're going. Inventory and logistics know that we just met minus 32 parts from our hub. So they now know that they need to come and bring more parts there. Tech brings his server, his machines outside, and he begins his work. He sits in a data center all day long. And he doesn't have to run end to end. Because again, we have 2 Walmart supercenters fit in each one of our buildings. It's kind of a bear when you, oh crap, I need that other hard drive. And you got to run over there and do it. But it's even more of a bear when you can't remember where the hard drive is, or you lost it, or you got to buy a new one, or you got an SRO guy yelling at you because his one machine that is, you know, by God and by golly, you know, the world's going to end if this one machine doesn't get back up, right? We decided we don't want to do any of that kind of stuff. So we got better and better and better. And with sort now, and our spares management, an important thing to bring into mind is this. Anything an internet company has, the one thing an internet company has with people, a lot of people call them users, we call them people, because that's what they are, is trust. It's trust. So maybe some of you guys work on security, you know, internet, network security, right? Cyber security, the whole thing. You know, data center is a big security protocol too. And those hard drives have data on them. It could be your data. We don't want your data out there. You don't want your data out there. The only thing we have, any company of any internet ilk, is all about trust. Trust from the people. So we manage and monitor hard drives, for instance. If you look again on the cart, there's a lock on the upper right-hand corner. Even in the data center space, a data center technician, the tool says a hard drive needs to be replaced. That data center technician scans that hard drive out, puts it into the cart, and locks the cart. Even in the data center, you're already through 3 levels of security. Then he's got a certain amount of time that he can keep that hard drive in his cart before the alarms go off, the bells and whistles. That drive has to change state and go into a room, right, where somebody else takes custody of that drive. And then from there, we take that drive and we try to eradicate all data from it. If we're unable to do so, we destroy it on site. We've got a couple of ways to destroy it. One's a, you know, pretty cool punch where we just basically, you know, punch the spindle, you know, and it makes like lots of little pieces, and it's kind of cool. But the other one is the chipper. Now, if you guys have never seen a drive chipper, they're pretty cool, right? You guys like that? I am like in love with that. I just love going like, yep, that's a certificate of destruction for me right there. Your data is safe, trust me, man. So we do that in the data center space. We take it very seriously. In fact, we run red alert kind of things where our software and our servers are working together really well with our technicians, and our data center manager will run out and pull the drive. Because we can, right? Because that one server doesn't really matter to the entire fleet. We pull a drive. How long does it take us to figure it out, right? Most of the time, within minutes, we know that something just happened. The drive's not there. We've never had a drive escape our data center space because of the software and the workflow that we put together within our data center space, along with physical security. These are important things. These are hard things. And it's a lot different than trying to figure out how much more drive space do you have on this one file system. Servers and storage, open compute, that's where we really started changing the game, right? What I'm going to share with you is like we saved $1.2 billion over the course of the last 3.5 years, right? $1.2 billion. Should have negotiated better, like on, hey, if I save you $1 billion, can I get like $500 million, But it wasn't me, it was a team, right? It was a whole team of people, and I wouldn't have been smart enough to do it anyway. But in reality, from an energy cost and savings, right, our total operational cost, right, is down 24% over a standard data center space. We're saving a huge amount of money on our servers. We're getting more compute per buck, right, than anything that we've ever had. So 38% more energy efficient. Let's think about that. Let's say I have 100 megawatts in the past, okay? 38 megawatts, which is enough to run 4 Prineville, Oregons, 4 of them, right? Out the window, gone, right? I don't want to lose that. I want to take that energy and I want to put it into the compute resources that I have. If I'm going to spend that money, I want something out of it, which is like a relative compute unit. I want to work on computing, not work on using energy and just putting it into ether. 38 megawatts worth of extra power, right, could go to somebody else on the grid. That's the power we don't have to generate and we don't have to make. When you think about green and you think about efficiency, we've talked a lot about the negawatt, and that's the energy that you never did consume. We still talk about that. We still look at that, and we still try and get better and better and better. While we're greening our sources, we're also becoming more and more efficient all the way through our stack. Even our power supplies are specified at coming in at no less than 95% efficient, right? Because when I translate, when I transform between AC and DC, right, I lose power. We don't want to do that anymore. So our servers, we said this from this guy's standpoint. We need to have the best serviceability. I need to be able to fix it quickly. I need no tools because, again, I kept losing my damn screwdriver, right? And so no tools. Server must be front of rack serviceable. If you've ever seen the rows, I'm in this server at this spot, and then I got to run out, go around, come back over, and I got to try and figure out where that server was in there and do whatever I got to do back there. Is that light blank? Oh, crap, no. And then I run around. You spend all your time, preparing for marathons, right? It's not that fun. So it's got to be front of rack serviceable, and we got to have simplicity in design to allow for our quick repairs. From the open compute standpoint, right? We're extremely efficient in server repairs, right? If you've ever worked on some of these boxes where you got to remove the entire Volkswagen chassis just to get to the motherboard or the power supply, and they weigh like oodles of pounds, right? And you got your little media cart, which we don't have anymore, and you put it on there and it like stretches and bows, and then it's pretty rough, right? We don't do that anymore, right? We changed. We went lightweight, highly distributed compute platform. So I was here. I was working with a guy named Amir Michael, and we started the freedom from the Volkswagen, right? Freedom from the sheet metal. Freedom from all those things that stopped me from being able to actually work on this thing efficiently. I need to put a caveat in here, though, and I want you guys to really take this one home. Just because I can work on something quickly and replace a proc in about 2 minutes and replace a motherboard in under 4 minutes, right? That doesn't mean anything. That doesn't mean anything at the end of the day, because I'm relatively inexpensive from an overall infrastructure standpoint. I don't cost a whole lot of money, so I get a lot of people. I don't care if it's 1 screw, 2 screws, 3 turns, half a turn. If I can replace a proc in 2 minutes, that's cool. If I can replace a hard drive in 30 seconds, that's great. But what if I can't tell what's wrong for 3 days? That's the bigger thing that needs to be fixed in our industry right now, right? This Freedom Machine, well understood by Facebook. We actually have almost no errors or alerts. We're already moving it out, by the way, because it's over 3 years old. My favorite machine ever, right? I put a postcard in front of that thing. It says 3B. That means the memory stick in slot 1 is bad. I don't have to take all the memory out and reboot only on that channel, and then put the other memory in and reboot. Oh, it didn't reboot. Then start moving memory through its slot and reboot 47 times to figure out what one stick is bad, right? Not cool, not fun. And you know what you have to do? You have to buy more servers and more infrastructure to keep your servers running, right? Well understood compute failure modes are really, really important. How many times have you had an HP server or a Dell server or any other store-bought server, right? And we still have them. We have great relationships with those guys, but let's be clear. How many times have you had one that's broken for 3 days and you can't figure out what's wrong with that array controller? Is it the cache array battery? Is it the controller, right? Is it the motherboard? What's wrong here? And then you troubleshoot it for 3 days, then you call in help, and the help comes in and they troubleshoot it for 3 days, and then you end up just killing that box, right? So I don't know, a week or 2 weeks have passed, right? You gotten your money out of that box? Have you done what you wanted to do there? Right? So I want to be clear. Just because we can service things quickly from an open compute standpoint isn't the be-all, end-all. What needs to happen now is have well-understood monitoring. When a server breaks, I need it to tell me what is wrong with it. If it can tell me what is wrong with it with a 98, 99% efficiency, right, we're going to be a lot better. We're going to be a lot better because we have to buy less because we have less in repairs at any given time, right? We're going to be a lot better because we're not spending all of our resources and our time trying to figure out that one thing. We can go work on some harder problems. Today, because of open compute, another guess or a question. How many technicians per server? Well, most people don't even like this metric, right? How many technicians per server do you have? When I started in Microsoft in the AT&T building in Bellevue at the old Moss West data center way back when, right? We had one technician for every 500 servers. Because again, I had the SQL Server and push-up thing going on. 1 to 500, and I was ragged, man. I couldn't keep up with that, right? So how many technicians per server do you think we have in the data center? It means people actually working on the break fix. They go to the ticketing system only, and they work on it. Any guess? You check that out. Most is 1 to 20,000. 1 to 20,000 servers. We only do that by running an entire stack from our software monitoring into the server and into the data center, right? Everything has to be known, understood, and interrelated. Tools should only work one way. There shouldn't be a way for me to violate that tool, right, and do it my way, right? When I'm running at scale, homogeny is important. You watched the Microsoft presentation at Open Compute in San Jose a while back, where they really, and I was so glad to see this because it wasn't that way when I was there, homogeny is the key. These servers all have to be understood, my failures have to be known, and my remediation has to be known, right? If we're going to go to scale, you got to do that. I want to go 1 to 50,000 server technicians. In one of my data centers, we occasionally bump up to 1 to 38,000, right? Just because somebody's on vacation or they're gone, and we don't do anything. We check it out. We watch and we see what we can do. But what it indicates is that whole vertical stack of software, server, and data center are working together the right way. And that's what we really look at all the time. So Freedom was awesome. Big triplet rack. Rule number 2 for you guys. This triplet rack, some other people might recognize that look. That was the first rack that we made. It was wide, it was deep. And we said the power draw in this data center is going to be about 6 kW per rack. That's awesome. 6 kW per rack. So we build a data center for that. Once you pour a pad, your concrete pad, you now are stuck with what you're doing. So you order your power, but you pour that pad. That pad doesn't get bigger, doesn't get smaller. The electrical distribution doesn't change. It can't change, right? So there it is. And then you come in and you say, oh, man, it's not 6.5 kW, actually. These are really efficient. They're only running 4. They're only running 4 kW. Well, heck, I'm going to strand all this power now, right? Like 25% of it, right? It's just, I'm not going to be able to use it. So we got really smart. We built that rack really tall. And for me, that was pretty awesome. I was like, God, it's about time, man. You know, I could reach out, grab everything. I even had to get a stool, but some of the other guys, they didn't like that so much, right? But that's what we did in Prineville when we're learning. We iterated, we tried, and it's like, it didn't work, you know? No harm, no foul, but then we had big fights about, okay, what does a rack look like from a physical dimension standpoint, and does it fit like in co-location spaces, because we're still there, because we don't want too many iterations of things. So then we moved on and we said, okay, let's go for some density. So then we go into our windmill, right? So, you know, our windmill was Sandy Bridge and Ivy Bridge? Yeah. And very, very similar to Freedom Open Compute, but now there's two of them in one tray, right? So my mind, server guy, was like, gosh, we just increased my failure domain by 50%. Well, let's go back to resiliency. It's probably okay, right? I want to increase my failure domain because that one little board there with 2 nodes on it shouldn't cause a problem for us. And we put these in 2012. Yeah, in 2012, every one of the servers we put in were open compute, right? We started in 2010. We started building our data center in, January 2010. We were done in December. And we did only Freedom machines in our front-end web services, right, in our cache, because does it work? Are we good? We don't know, right? We don't want to upset our users, so let's go with what we know there, but let's go in on this and let's see if it works. It worked. Next thing you know, we're like, hey, let's go to windmill, right? And then we started going, hey, we could do even better. And this is where I'm like throwing my hands up, I'm like, why? Why? Is good enough, right? Why do I need to increase density? I want to increase lightweight, highly distributed compute systems because I don't want to freak out every time that you have one of these fail. And every time one of those fails, now 3 of them fails because I'm sharing power supplies, I'm sharing backplanes, I'm sharing fans. But you know, somebody showed me the money one day. Rule number 2, always follow the money, right? They showed me the money one day, and it's like, oh my goodness, at the scale that we're at, sharing a power supply is a huge, huge cost savings. And I can take that money and I can build more infrastructure with it. So if you look at what we've done with Winterfell and OpenRack V1, which basically shares, you know, a common power supply through the back, you see the 3 zones there? We basically plug these Winterfells in and they have a blind mate snap-on, and that's my power supply, those rails in the back. It's not a bad machine. I was really against it because I'm in love with freedom. I don't want to change. I want to keep freedom. Fortunately, I don't run the whole business by myself because we'd still be running freedom and we would be falling behind. We've increased our compute power. We've increased our relative compute units. We've continued to drive down our cost in servers and infrastructure. And we've continued to increase our resiliency through following this model of the stack, the software and the server and the data center working together. So now what's coming out is Leopard. It's on the way. You guys are going to hear about this really, really soon. If you haven't, we have a brand new motherboard design, and it fits both OpenRack V1 and OpenRack V2. So I don't have to change my infrastructure so much. That's another problem in the data center space. Every time somebody gets smart and they want to change something, I got to rip all this stuff out and put in new stuff. It costs a lot of money, right? And then you know what else you do? I got to talk to all of you guys about like, hey, I need to take down this row. You're like, oh, very important row. I can't do it. I'm like, well, wait a minute. We have to do these changes. So we have this yin and yang and negotiation thing going on, and we all have to work and jump through hoops and all kinds of other things. What we want to try and do is stop that from happening. So go back to Cluster Planner, right? We go to Cluster Planner. We all work off of that now, and we share with everybody what's going on. So very, very, very early in the planning processes, SRO, SRE, application owners, they can start planning and managing their change. So when the change comes, it's nothing, just another day at work. Gives me more time to watch football. So Leopard is coming our way. We're really moving that way. These racks we expect to see in the data center space for a very, very long time. So now we're starting to think about different things in the world. Like, what if I had like a rack wall, right? The wall had network and power built into it, and all I had is these little sleds that look like the form factor like this. This is our decided upon and agreed upon form factor for us, right? What if all those sleds were basically just color-coded and you just told me how you want me to put the rack wall together? I want so much compute, so much memory, and so much hard drive, and it's all highly distributed within the wall at construction time. All of a sudden, I'm not replacing all of it. I'm not dealing with any of the power grid associations or anything like that. All I'm doing is like, I got my I could actually do this now. That's actually cool. I could look at my Excel spreadsheet and go, oh, okay, I got 14 reds, 3 greens, and 2 blues, and I just go shove those in there. And what if the future looks like, well, then I do X, Y coordinates, and I have like a Roomba coming through there and just yanking them out when they fail and putting a new one back in, right? It can happen. But these things don't happen unless you think about it. You know what? Now that I think about it, I got to segue for a minute. What was that thing that just happened today? We just put a lander on a comet, and it just happened, right? Right? Huh? How killer is that? When Star Trek came out, they were talking about Nextel phones. You remember that? Little Nextel. The movie Armageddon actually landed some people on an asteroid too. If you don't think about it, and if you don't dream it, it's not going to happen. That's the point about this, right? Think about it. Good enough's not enough. Open Vault. Have you guys heard about our cold storage ideas and what we're doing with that? Just a bunch of disks. I need to know which disk has failed and when it's failed. We need to not have so much power draw. So let's put it this way. Nicole, ski instructor type, you know. She's out ski instructing, taking some cool pictures of herself doing, everybody's liking it, and everybody's looking at it, and it's a hot picture for a while. And that's what we call it. We call it hot because everybody's looking at it because it's new. But then it gets cold. It gets a lot colder because once you've seen it and once you've liked it, it's like moving on to the next one. But you know, Nicole, it's still your picture. And you still have access to it, and you should still be able to see it anytime you want. And if somebody's lurking on your page, they get to go, sniff around, and they get to pull that up, right? As long as you're friends with them and you set your security policy correctly. So at the end of the day, caveat. At the end of the day, the real important thing to understand here is that that's yours. And we have a duty to keep it for you, and to keep it safe for you, and to have it accessible to you when you want it. You guys all know this. Data is expensive. Those big boxes and those big drives and those big things that we got to keep all this data on is expensive. If it's not hot data, I need to figure out a cheaper way to keep it because it's too expensive, right? So we come up with what we call cold storage. We actually even built a building specifically for it. It's a little less resilient than a data center because it does need to be. Generally speaking, we have a huge bunch of disks with a compute node on them, right? In one rack, we have 2 petabytes of data capability in one rack. That's pulling like 2 kW, right? Wow, that's pretty cool. Now we're trying to figure out how to do that from a software perspective and how to make it all work right, and we're working on it right now. We're going through it. And while we're doing that, we're already thinking about, that's pretty expensive too. What if I use Blu-ray? Right? What if I just have these Blu-ray discs, this big array of them, and what if they dropped out? Well, you put them all back in and just reorganize it, and it just takes care of itself. What if we do that? So we're working on things like that because, you know, at Facebook and in open compute, good enough is not enough, right? Good enough is not enough. This is very simple. There's a guy in our audience right now who's working very, very hard on this. Right? To make this a reality, to make it truth, but more so to make it supportable, which is going to make it real. So rack configuration types are really important. It should be known, I'm going to do another caveat here. We have 6 rack types. I know it says 7, but you'll notice we're missing a 2 because we figured 2 was redundant because it looked just like 1. We're like, why are we doing that? But in reality, we have really 2 rack types. We basically have the capability to take compute nodes and storage medium and put them together in different configurations to create the other 4, right? So what we're really looking for here, folks, is the fewest number of machine types and iterations that provide the greatest number of, or the greatest value to the application, right? So for instance, if you yourself say, I have a lot of compute, but I don't need a lot of memory, and so you try and make something specific for you. By the way, there's 2,500 of you that have all your little things. And then, so you make this, and you make this, and you make this, and then you ask me, how come you're not supporting this in the right way? How come you're not doing what I need, right? We can't, right? That's not scalable. So what we did is we said, okay, generally speaking, and within these bands, we have this much compute, this much memory, this much storage. Here's how we're going to be allocating it, right? There's other people that are working on, you know, things like Borg type of systems that disaggregate. I mean, AWS is a good example of that, right? You're disassociating the compute from the application. And you just basically say, hey, I want to buy some of this and buy some of that and use some of that. So this looks really cool. I should tell you, though, that I don't look at it quite as cool as it could be. Because in those 7 different configuration items, if you move one processor, if you change one memory configuration layout, if you have this ROM or that kernel or that BIOS setting, that is a completely different fault domain and a fault profile. It all changes, right? So when you really start thinking about it, looking at your domain that you support, that you run and that you manage, look at it side by side. Just how you used to figure out when Windows load balancing was working, you take all 3, put them side by side, and if you saw any difference in the line, you say, there's a difference here. This is the same thing. If your computers, if your servers that are out there on the floor have a different BIOS setting and configuration, if they have a different ROM, if they're running this proc over that proc, if they're running this memory over that memory, they are a different fault domain. They're a different failure profile, right? And the people that are trying to fix that for you, right, they have more problems. And the more of that you have, right, the longer and harder it is going to be to keep those machines online so you can get back to doing what you do. So then we moved into the data center space. It's like, my favorite thing to talk about. And I really, to be frank with you, I thought about I should put a movie on here and talk for 5 minutes and then just do a 45-minute movie. That would have been cooler. But we looked at our data center space. And like I said earlier, right, we've saved over $1.2 billion by thinking about a vertical stack of software, hardware, and the data center space. Network's in there too, so make no mistake. There's a lot of underlying things. But in the data center space, we went to Prineville, Oregon. We wanted to use evaporative cooling because, as you know, evaporative cooling basically just takes free, natural air, or naturalized data center, a natural air, right? Just brings it in, puts it through the data center. For 8 months out of the year, Prineville, Oregon actually provides us that capability. So all we really got to do is suck air in. That's it. That's it. By the way, one of the things that we do, though, is really interesting. Our kernels are now on our servers that are looking at the pressure differential between the hot aisle and the cold aisle. And the fans ramp up or slow down so that the air can dwell on the processor as long as reasonably possible and provide the maximum cooling efficiency. This is how the hardware and the software and the data center is working together. Before that didn't happen. Right? You just, had your mechanical chillers and you had, raised floor tiles that would blow your skirts up, in order to keep the servers cool up here. But these guys are icicles down below. I mean, these were tough days, tough days. We've done this same exact data center design, almost, in Prineville, Forest City, North Carolina, Luleå, Sweden, and Altoona, Iowa. In fact, tomorrow, I'd like to stay and hang out with you guys, but I'm going to the grand opening of the Altoona, Iowa data center tomorrow. And it's going to be a cool deal. That's a huge data center. There, you can fit 2 Bass Pros into theirs, right? Bass Pro's a little bigger than Super Walmart. It's a pretty big deal. And Bass Pro's across the street, too, so it's pretty great. So at the end of the day, we decided to make some real fundamental gambles, right? We're going to build our buildings. We're going to try and be as efficient as we can. We're going to own our own destiny. And we're going to do it in these kind of places. And we're going to do it by founding the Open Compute Project. Because we think that what matters is how your bits run on the wire. That's your secret sauce. That's what's really important, what your application makes and what it does. Getting it to the masses is everybody's problem. Getting your application to reach people, right, everywhere in the world is all of our problems. So how do we do that? We can't do it by overspending. So the industry standard, basically, you use power however you got it. You mechanically cool and chill it and shove it into your building. And then on the far right, you start stepping down from a power perspective, right? Because you take, let's say, 13,500 kVA from the wire. You come through your PTX, your transformers, you drop it down. Then you go through another step and you drop it down. Maybe you're 220, maybe you're 110, right? Into the data center space. And then you go through your power supplies. Drop, 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 drop. Very, very big loss of efficiency. So what we did is we basically took the outside air from our grid, in Prineville, I should say, it wasn't as green as it is today. When we started, we just took, power's a swimming pool, and you plug into it and you get it. You can do other things like buying RECs and doing all kinds of fancy things to try and, pretend like you're green, but we don't want to do that. We want to do the right thing. We want to make a difference. Like Altoona, Iowa, 100% wind-powered data center. 100%, right? Luleå, Sweden, all 100% hydro. Thank you very much. But you can't start that way. It takes a lot of work. All of our data centers, the green arrow and the little box there, which is a data center, basically suck air into the data center, move it through some rooms, drop it down. I'll show you that picture in a minute. And then the only way it gets out of there is it goes through the servers. It dwells on that processor until it takes all the heat off of it, which heat, by the way, is used energy. We're going to need that in a minute. And we get a 1.07 PUE. Right, think about this. Just think about 2. Think about 2 PUE. When I started in this industry, they were a lot higher than that, and PUE didn't exist. Power usage effectiveness. People know what that is? Okay. So in case you don't, it is basically a ratio of the amount of power that you bring into your building versus how much you actually use for compute, right? So for instance, on a 1.07 PUE, nearly 100% of the power that comes in is used for the servers. I've got a 99.03% of the power coming into my data center is used to provide compute, right? The 0.07 that you see is how much it takes to run and manage our building. If you've ever watched some of our videos and things like that, you'll be walking through and you'll be like, where's all the machines that move the water? And we don't have those. What's really cool about what we've done is you don't see it, right? It's what you don't see that's the magic. So here's the way this works. Typical data center cooling. At the top, you got a cooling tower, you got a chiller, you got air handling units. All of those, by the way, have motors, and they're sucking power and their energy. And everywhere you see a blue and a red together on the top, you're basically losing efficiency in cooling, right? Because you have the hot water going by cold air, and it's sucking all the air out of it, making the water colder, and it just keeps going in this endless loop. And if you guys ever have a swimming pool or a hot tub, you realize how much energy actually costs, pushing this water around. That's a typical data center nearly everywhere. And in some places, you simply have to do that. You have to, right? Sometimes you can't get around it. You got cracked units on the wall. That's the way it's going to go, just based on where you're building. So that's important, where you're building. What we did in our Open Compute Data Center, if you look on the left, the outside air intake, it comes through a filter wall. So that's just a bunch of filters, right? And then so no motors, comes through this misting system, right? We have 2 different kinds of misting systems. We started with a reverse osmosis system that came out, because think about like a hairspray nozzle, and it just aerosolized the water molecules, and you just suck the air through it. So it's like hiking underneath a cloud. It gets really cold, right? At the end of the day, that was good, but RO, it's expensive. It's expensive to put in, it's expensive to manage, it's expensive to maintain. So then we moved into a Munters media system, which basically we just move water right from our well, and we just trickle it over this media, and we just suck the air through it. So what we do right now, and we're more than 35% more efficient there in building 2 in Prineville than we are in building 1 with the water usage effectiveness. But we still, with our whole data center space, in the high desert, which is Prineville, Oregon, by Bend, we use about 29 gallons a minute on average, right? The fire hose place and the laundry down the street, which is a postage stamp compared to our footprint, they use 60. You know what I mean? That's good. So not only are we dealing with PUE, we're also dealing with WUE, the water usage effectiveness. Here's the important thing, busy slide, and I would love to get really technically involved in that, but just somebody in this room would probably kill me. Here's the big thing. See all that green over there? That's where we don't step power down. That's really what this is showing you. When you come into our data center, you see the 13,500 kVA transmission line moving to a 480-volt PTX. That 480-volt transmission, that's my step down, comes right into the building. And it goes right into my bus duct. And I just tap off of that, and I got 277 volts going to every server, from a 480 volt. That's what we've got. We don't step down. Same thing, UPSs, people talk about inline UPSs, and some UPSs convert and then reconvert and the whole thing. You lose efficiency every time you change or modify your power. We do it once coming in, and then we do it once at the power supply. Our power supplies were some of the first. They take AC and DC. Industry didn't support that. Nobody wanted that. It's part of the Open Compute Initiative. Now, right, if I lose AC utility, I run on DC, right, for 90 seconds while I wait for utility to go, and I wait for my building to change, and I wait for my building to bring new power back. As soon as it senses AC is there, it stagger starts, goes back to AC. Now, we did screw that up. We forgot to do the stagger start, so inrush, man. You drop it, and they would all come back at once. It was like, kaboom, right? And then breakers would blow all over the place. So we learned and we iterated, right? We don't have these problems anymore. Here's the story at the very bottom. All the way to the server, you can lose up to 27% of your power. Again, think about just round numbers. Think about 100 megawatts. That's 27 megawatts of power that you're buying and that you're not getting what you pay for. And you're not being green because you're wasting it, right? You're throwing it away, right? It's not efficient. 7.5% total loss to our server in our current buildings, and it's getting better, right? These battery cabinets, when I talked about it prefers DC, right? This is how we started with these DC UPSs, or VRLA batteries sitting in there. The rack, there's 2 racks, one on either side, the triplets that you saw earlier. If I lose utility, that rack is a micro segmentation of a failure domain. That DC UPS will support those 2 racks until the power comes back, or 90 seconds, whichever comes first. We really want the power to come back, right, within that time. If it doesn't, I lose those. Or if there was a problem in one of those batteries, I just lose those 2 racks, right? In the old school, the DC UPS model with dual bus, redundancy, and all that other stuff, just like everybody else that has a tier 4 data center do. And that old school, what would happen is you would be going through UPS, and there would be one battery in the string that's got a bad cell, and you would carry your load for 0.09 seconds before your entire data center went down. Which one do you think is better, right? Resiliency. So I want to wrap it up, and I want to really get to the point. Our stacks, our optimization, they all perform together, right? We expect to be 3 times more efficient really soon with our servers. We think our data centers are going to be 5 times more efficient than what they are today, very, very soon. We created a symbiotic software stack. We want to manage our data center. We want to continue to iterate on it. We looked at our workflows. We looked at our efficiencies. We got rid of all the sacred cows that we could. And we said to ourselves, hey, good enough is not enough. And what we did in the past isn't good enough, right? We engaged very, very deeply in Open Compute. We gave the first 3 designs to it, right? We're leveraging that. We're getting information back. We're giving information. Other people are starting to change the world with their applications because they can now afford to actually do that, right? So we decreased our complexity. You can see that from the green in our power supply grid, right? We saved over $1.2 billion. $1.2 billion is a lot of money, right? We want to maximize uptime and availability. We want to focus on building all of our great products. And we want to connect. We want to connect the next several billion people. In order to do that, technical debt must be kept in check. Manage your application weight. Manage what your application is doing on the wire, and know, right, that it matters. It matters because you won't have the money to expand, right? You can deploy more globally this way. You can reach more people. You can have a bigger impact, right? You got to think differently. You got to really think differently. And you got to ask yourself, right, is what I'm doing, right, is good enough enough, right? You want to know more about that? You can go to opencompute.org. You can check it out. And now, if there's any questions, I'm 2 full minutes over because I just can't stop talking. If there's any technical questions, I'm just going to defer. On?
The mic's on, that's fine.
I'll repeat it.
So it looks like you're getting more and more modular, more automated in terms of how you can prepare and replace your pieces of hardware. How long it is before your entire break-fix cycle on the system side gets robotic? When do you foresee robots swapping out like car
Got it.
parts?
The question is, we're pretty good at what we're doing now. When are we going to replace human beings with robots, right? When are we going to go all dark data center and do robotics? We're thinking about that stuff. We're looking at RFID stuff right now. We're making slow and stepped iterations on it. We're thinking about it. Time frame? I don't know. we're going to give it a shot. We're going to think about it. It's like I talked earlier. If we can go to, let's say, an open rack wall, right, and all I do is put in modules in and out of there, we might be able to get there. So we're thinking about it. We don't have a time frame. We don't have a live project. We have us going, could we do better? That's where we're at right now. Sir?
Great presentation, thank you. What other chip architectures do you think are going to be relevant in the not-too-distant future? I assume you're largely all x86 based. How do you see that as a plus and or a liability?
I actually couldn't hear you very well.
Okay.
Anybody else can? Regarding risk-based processing? Okay. So again, just like robotics, we're talking about that. I think it would be great. Risk-based processing is cool. We've got some other applications that are out on Open Compute that basically take compute nodes and turn them into a little PCI card. It might be that kind of direction that we go. So we're looking at that right now. So who knows how fast this stuff moves. We want to do it through Open Compute, though.
Thanks.
Yeah. Sir?
No, it's not. Okay. How much of what you're doing here is going to be of benefit to people in smaller shops? Like the ability to repair hardware is great,
yeah.
But if you are, let's say, a tenant in a data center and you're not the one going up and sort of getting stuff, we're not able to buy these things from Supermicro. When's that going to happen?
Okay. So that's a really good question, and it's something that we actually talk about a lot. Like, how does a smaller shop actually benefit from this kind of thing? I think one of the things that I started with is small shops actually benefit in that they've got to do a lot of things that we look at and go, hey, maybe that's a better way to do that, right? So it's actually the reverse of what you asked. I think what happens from a smaller shop standpoint, this is Ken thinking out loud, the fundamental difference is if we can drive compute cost way down, the smaller shop can now afford compute cost. If we can get people that actually say, hey, I'm going to qualify your application on open compute hardware, and there's an open compute data center that exists so you can put it in there, or you can keep it in your own closet, right, if that's what you want to do. I think the fundamental premise is simply this. If you're a small shop, you can afford it. You can't today. Unless you're a rich small shop. Anybody else? Good, because we got to get out of here. Thank you all for your time. I really appreciate it.